Hello everyone, in this video we're going to talk about the frequency response of our system. So for a linear time invariant system, the frequency of input and output is the same, and only we have a change in magnitude and phase. So if our input is A1 sine omega t, our output would have the same format, only the amplitude has changed or the magnitude has changed. The frequency would be the same. Also, we have a phase change. So here in this example, if you look at the input signal and the difference between the output signal, the amplitude has changed, but the frequency, if you measure the frequency would be the same. And also we have a phase change. And here is an example of showing that with a change of amplitude, but the frequency would be the same, and there is a slight phase change. We said that is true for linear time invariant system, and in many cases, the systems that we are looking into are linear and time invariant. And definition of linearity is the same that we define for differential equations. We shouldn't have any nonlinear component. Or if you scale the input, the output will also scale. But you need to remember that when we are talking about linearity, we are talking about a differential equation. So this differential equation would be linear, but if you take a Laplace of that, that would be s squared xs plus s, and this would appear as nonlinear, but that's because we are in Laplace domain, and then the criterion applies for the differential equation itself. And the other condition was the time invariancy. As the name suggests, the property of our system should not change with time. And in many cases, practical application, that is true. But you can think of suspension system that the property changes with time because of wear and tear. The K could change with time, the damping coefficient could change with time, the mass could change with the time. And that would be an example of a system that is not time invariant and it changes with time. In that scenario, then our transfer function is going to have a component as function of time, which means that our transfer function changes with time, which is not really common, but it could happen in real application depending on how accurate you want to be. So here our job is to find the magnitude and phase, because we said that A2 is going to change with respect to A1, and also we are going to have a phase change, but the frequency would be the same, and that's the condition of time invariant system. How are we going to find this change in magnitude and phase? Our first step is to replace S with j omega in our transfer function, and we are going to find a magnitude difference, or A2 over A1, by just finding the magnitude of transfer function now that we have replaced S with j omega. And it's going to give us a complex number, and if you want to find a magnitude of a complex number, we have to use Pythagorean theorem for the real and imaginary part. You can think of it as in our coordinate system. If this is a complex number, and then if you want to find this distance, we need to have the real part squared plus the imaginary component squared, and then take a square root of their addition. If you want to find the phase change, then we have to find the tangent inverse of the imaginary component over the real part of our system. So for frequency response, our job is to find this change in magnitude and change in phase, because we know the frequency is the same. But this change is frequency dependent, so we are not going to get one value for all frequencies. For every frequency, we are going to have a different MW and PW. Let's look at an example to better understand it. Let's say we have a transfer function, this GS here, and we want to find how the input and how the output is changing with respect to input. And the problem wants us to find it for a range of frequency, not a specific frequency. So we're gonna solve it symbolically as function of omega and then replace omega with a range of values. So the first step is to change s to j omega. So here, instead of s, I'm gonna put j omega. That's all I need to do, and that's what I get here. Then the second step is to find the change in magnitude. So mw, which is the same as the magnitude of our transfer function after we replace s with j omega. And we can find a magnitude with the real and imaginary part. Here they're in the new denominator, so that we place them in the denominator, and the real part is this 10 so that I have here, and the imaginary part is omega. So that would be our mw, or change in magnitude. I don't have a specific value for omega. I want to find it for a range of omega, so I keep it as is. The next step would be to find a change in phase for a given frequency. We said change in phase would be tangent inverse of the imaginary over real component. We have 0 here at the beginning because the numerator angle is 0, and then minus the angle of the denominator, which is that omega over 10. So now we're going to find it for a range of frequencies. So this was our transfer function. We said that we have the magnitude. We found the magnitude would be 1 over a square root of omega squared plus 10 squared. And then we can change that into decibel. That's a common approach to change the magnitude into decibel. And then the equation for that would be 20 times log 10 of the magnitude. And MATLAB does the job for us. We can use function magnitude to decibel and decibel to magnitude to simply change the values, or we can put it in our calculator to convert from the magnitude to decibel. And then we have the change of in phase. That's the equation that we found. Now we're going to put a range of frequencies. If I put a frequency of 0, if I place 0 here, I will have 1 over 0 plus 10 squared, so 1 over 10. That would be the magnitude. And if I want to find it in decibel, then I have to say 20 log 10 of this magnitude, 0.1. What would be the value? I can find this first, log 10 of 0.1. That means that 10, I have to raise 10 to negative 1, so to get 0.1. So that would be negative 1. 20 times negative 1, that would be negative 20. And that's what I have here. And that's for magnitude, that I can present it in a magnitude format and in decibel format. And for the phase, I can plug in 0 here, and 0 minus tangent inverse of 0, which would be 0, so my angle would be 0 degrees. And that's the angle I have. Then I can plug in 10 for my frequency, and I can plug in infinity, and I get the range of values for magnitude and phase. And I can plot these magnitude or for a range of frequencies, saying that how will my magnitude change over a range of frequencies, and then observe the behavior. I could do that for a range of frequency for the phase as well. If I do that, these plots are called Bode plots or Bode graphs that we can have that have two components, a magnitude component over a range of frequencies and a phase component. So they immediately tell us how our system or our transfer function is changing with a range of frequencies. The magnitude is usually expressed in decibel, and in logarithmic scale. We use logarithmic scale so we can cover a large range of values. And the phase plot can be reported in degrees and radians. You can change that, and basically tells us about the phase change of our system. MATLAB again has a useful function for Bode plot, and the name, surprise, is Bode. So if I want to find a Bode plot of this transfer function, 1 over s plus 10, all I need to do is that use the numerator in bracket and denominator in bracket, and then it will result in this plot. So this plot tells me how the magnitude is changing in terms of decibel and how the phase is changing for a range of input. My input can have any frequency. So for a specific frequency that you are interested, let's say for a frequency of 1, you can come and find the phase change and the magnitude change.